Okay, so we're in the projectile motions notes and we're looking at the first example, which is a tennis ball lobbed horizontally from a height of 2.4 metres at a speed of 40 metres per second. So what time does it take to reach the ground? So let's draw a little diagram. And we have the tennis ball at 2.4 metres above the ground, and it's hit at 40 metres a second horizontally. And we also have acceleration due to gravity of 9.81 metres per second squared downwards. Okay, so the ball's going to take a projectile motion path, so the path of a parabola, something like that. And we're just going to, in this time, they've asked what time does it take to reach the ground, so we're just going to concentrate on the vertical components. So S, U, V, A, T. S is equal to 2.4 metres. We start off with 0 metres per second in the vertical, sorry. It's in the vertical, so it's just like a ball being dropped. We're not sure what the final velocity is going to be. Acceleration is equal to 9.81 metres per second squared down, and T is what we're trying to find out. So we can use S equals UT plus a half AT squared. So then putting what we know, 2.4 is equal to 0 plus a half times by 9.81 times by T squared. Okay, so we can rearrange this, so we get 2.4 times 2 divided by 9.81 is equal to T squared. So T is equal to the square root of 0.4893, and then T is equal to 0.699 seconds. Oops, that's not a very nice 9. Handwriting is failing me a little bit this morning. 69 seconds. Okay. I'm just not confuse that with the next bit, so 0.699. Okay, so the next part, they've asked how far horizontally does it move before it reaches the ground. So this time we're going to consider our horizontal components instead. And we're not sure how far it goes. We know that this is 40 metres per second, which means that our final velocity is also 40 metres per second because our acceleration is equal to 0. And time, it takes the same amount of time for our ball to hit the ground in the horizontal and the vertical, so 0.699 seconds is our time. Now we just use S equals UT plus a half AT squared again, and we don't know what S is, that's what we're looking for. We know what U is, 40, we know what T is, 0.699, and we know what A is, that's 0, so that all becomes 0, and then this is equal to 28.0 metres in the horizontal. And let's put in it's a displacement, or how far horizontally, not necessarily displacement, but we'll say it is, so forwards. How far is a bit ambiguous, it might be a distance there, so you might get away with just putting 28 metres. What are the vertical and horizontal components of its velocity when it reaches the ground? So if we look at the vertical first, we've written our suvat up here. So I'm going to put a star in there. And we can now use V equals U plus AT. U is equal to 0 plus 9.81 times by 0.699, and that's equal to 6.86 metres per second downwards. And we've got our horizontal, which we already know, but we can go through the maths anyway. V is equal to U plus AT. V is equal to 40, and let me put my VV and VH in there. 40 for our U and plus 0 for our acceleration, so then VH is equal to 40 metres per second forward. Alright, so what is its overall velocity magnitude and direction as it reaches the ground. So it's a vector sum, like we've done before. So we have our horizontal velocity of 40 meters per second, and we have our vertical of 6.86 meters per second down. So our overall velocity is going to be our resultant vector. So I'm going to say V total, the overall V total, VT. Sometimes it's just uses VT as well. So we're going to have Pythagoras theorem to work out the magnitude. So the square root of 40 squared plus 6.86 squared is equal to 40.6 meters per second. Now we need to figure out the direction, and that's why we have our theta in there for our angle. Theta is equal to the tan to the -1 of opposite over adjacent. The opposite here is 6.86, and our adjacent is 40. So that is equal to 9.73 degrees. And we can say that this is below horizontal